Okay, so welcome back for the last lecture of today. Same as Monday, it's the last lecture, but show that you are engaged and ask a question and contribute to the talk. So it's my great pleasure to introduce Professor Bassam Dally, who is a professor at KAUST, and we will talk about novel applications. So this is a promising title. Make us dream about novel application.
Thank you, Diana. Welcome all. It's good to see external visitors, and we thank all the other lecturers who came in to share with us some of their wisdom. So Diana chose the topic, and then I tried to put a presentation that suits the topic. And then I thought, well, I'll just talk about what I do, because that's the way she describes it. So, okay, this is what I'm going to do today. I'm going to give a general introduction. Those who were in ASPEC may have seen the slides before, but I thought it's important to set the scene, and happy to sort of discuss it further. I'm going to talk about mild combustion as part of this novel application, steam calcinations, hydrogen peroxide, and then I'll leave you with some final words. So let's delve into it. Everybody wants to save the world. Everybody cares about sustainability, but everybody misses the point that sustainability has three pillars. It's the environment, it's society, and it's the economy. And of course, the environment is the most critical these days because of obvious reasons. But when we do it, in other words, when we talk about sustainability and we want to save the environment, we need to also think about other things. And we as engineers have been ignoring the other components. So cost matters, people matters, jobs matters. So we need to look holistically at things, not just focus on one thing. So that's my message number one. Now, energy and sustainability. Why is energy such an important thing and a lot of people focusing on it? Because you could see in here how important energy is and how important combustion to energy is. You could see in here that 82% of the energy produced comes from combustion. And this is why this course is important. This is why the field is important. This is why there's a lot of work to be done between and here. So this is for the year 21. This is for the year 2050 of what the International Energy Agency have said we need to keep the temperatures at 1.5 degrees. And if you look at combustion, it will still cover 50% of the energy we need. So then the key second message is that combustion is key to sustainability. In other words, without combustion, society, the economy will not survive, and the environment as well. So what's all the fuss about? If we look at the global warming and the greenhouse gases, you could see that energy is 73.2% contributor. So that's why energy is important. Now, if you take this 73%, and you have the 82%, you could see how important combustion is to the environment and to the sustainability in the future as well. So there's other contributors, as you could see in there, agriculture, forestry, and land use. That's something we could do something about. Waste, and then industry. And later I will show how there's emissions from industry that's not related to energy particularly. But in the outer circle, you could see that the contribution of different sectors, which I'll zoom into in a minute. And if anybody has any doubts what the issue is, of course, this is the CO2 emissions from 1949 until here 2020, roughly. And it's steadily increasing. And you could see here all the different summits that have been happening over the years. One could say, well, it wasn't effective, and one could also argue it could have been worse. So let's keep that in mind. But another thing to keep in mind is that between 49 and 2020, the world population increased threefolds, and the GDP per capita increased threefolds. What this means is we're going to use more energy, and which means that we're going to emit more. This year alone, or this is the first year ever, where of course after COVID, where the CO2 has not increased. And the reason it hasn't increased because the demand has increased by around 8%, but the increase in deployment of renewables has compensated for it. So there's signs that there's a tip-off point that's coming in. Again, in here on the right, you could see that the 7 warmest year on record are in the past 10 years. So we do have a problem. So I won't go into a lot of details in here, but this is a study from the Nature Communication. Basically, many scientists who use 6 different models to try and predict what's going to happen by 2050. And basically, they all conclude that with the current policies, we're heading to 2.8 degrees Celsius by 2050. In other words, we're not going to meet the 1.5 degrees target. In fact, we are going to reach that by 2030, if not earlier. Which then means as well is that we need to do adaptation, and that mitigation alone is not going to be sufficient because we need to be able to survive. Remember, when we're talking about sustainability, community matters, okay, economy matters, as well as the environment. So we're heading to 2.8 degrees, which also means that we're not going to reach the 50% contribution of combustion, which means combustion is going to be anywhere between 82 and 50. Okay, so combustion will still be needed by 2050. So why do we have a problem? Here they will try to assess the different sectors that are contributing to global warming, and where green is good, we're doing enough. Yellow is we sort of doing something, and red, we're not doing enough. And you could see in here that industry, transport, and the fuel supply are a major problem. I'll touch on fuel supply in a minute. But most of work is focused on industry because not many people talk about it, and I'll tell you why it's important in a minute. Another thing I'd like you to note is that in this figure in here, if you count the amount of CO2 that's being emitted, you could see some negative values. And where are these negative values coming from? They're coming from NOx and from SOx. NO and NO2 and SO2 and SO3 and so on. And we are trying to reduce NOx and to reduce SOx, yeah? Now the HFO is going to be desulfurized for marine transport. Coal is going to be used less and less, so there's less NOx. So if we remove these, the planet is going to warm up. We maybe need to thank China and India for keeping the planet cooler. But what this really means is that we need to cater for this amount of CO2, not this amount of CO2 in the future. In other words, the problem is bigger than we think it is. Now, talking about the fuel component, when you extract oil from the ground, you also release natural gas. This natural gas can be easily capped, but it's not. You could see in here that 130 billion cubic meter of natural gas is flared in last year. We said 130 billion cubic meter of natural gas has been just burnt and sent to the atmosphere. Wasn't used. This is equivalent to 350 million tons of CO2. Now, and it's responsible for 40% of the annual black carbon deposits on the Arctic. And what happens when this black carbon deposits in the Arctic? It absorbs more radiation, which means the Arctic is going to melt. So, and you look at the offending countries, I mean, who's who? But you could notice is that Saudi Arabia is not here, UAE is not here, Oman is not here. So there's a lot of the Gulf states already capped their emission, and they use their natural gas. So technology is available. It can be employed tomorrow. It will have direct impact. Okay, it doesn't require a lot of investment, and yet we're buying electric cars and investing in hydrogen. This has priority. Now, if there's any good news, is that there is a treaty or an agreement that by 2030 they want to minimize flaring or stop it. Now, if it happens or not, that's a different story, but I'd like to draw attention to this. This is important. Now, when we talk about industry, remember industry box was all red, yeah? So if you look at where the energy, 32% of our energy comes from, is for industry, but 74% of that is in the form of thermal energy. And then if you then look at what sort of energy in here, you found that 48% of it is at high temperature. Okay? Now, high temperature requires combustion because you can't do electrification because there's a lot of other ineffective systems to be able to use. But so when we're talking about industry, then you need to think about heat. Okay? And here there's a lot of it which is at high temperature. And here's the different processes by which they use this heat. So keep that in mind as well when we talk about industry and the use of combustion. And let's talk about everybody's favorite topic, cars, low-duty vehicle cars. This is basically battery electric vehicle, and this is internal combustion engine. Now, over 20 years period, this is the CO2 emission, and there's a factor of 2 here. There's a factor of 2, and you look at the uncertainty in here in terms of the calculations of what their CO2 emission is. So if we do that, we come and say, well, we're not too far off, actually. Now, to be able to run electric cars, you need new networks, you need new powering stations, you need batteries, you need electric motors. You need quite a lot of new infrastructure for electric vehicles to become viable. But we have all of that for the internal combustion engines. The only thing what we need to do is to reduce the amount of CO2 from that engines. Are we good at this? Well, we are. This is what the research has produced over the years for passenger cars from 2000 to 2020. And you could see we went from 200 down to around 100. So, and we could go further. We could add supplements to the fuel, ethanol or biodiesel and so on. We could do hybrid cars, which then will help in the fuel economy. We could even improve the internal combustion engines further. And then we could reach this actually relatively quickly without needing to invest literally trillions of dollars of new infrastructure. Remember, if you want to replace every petrol station with an electric substation to charge all these cars, how big this substation needs to be, where's the electricity going to come from, okay? And how much it's going to cost and who's going to pay for it. Here's an interesting case. Sorry, Diana. So France bought these electric cars for their civil servants. When batteries died, they couldn't afford to replace them. The contract with the employee was terminated. No one else wanted to buy them because they are high cost to maintain. I mean, is this sustainable to you? I doubt it. Now, I'm not against electric cars. Electric cars have a place to play. But if you're in Norway, it makes a lot of sense to buy an electric car because 95% of your energy comes from renewables. But if you're in Saudi Arabia, and when 1% of the electricity comes from renewables, then it doesn't make sense. Okay? We need to decarbonize the network first before we actually go on and buy electric cars. And hence, combustion will still be needed. That's the point. All right, so what do we need to do according to IEA in terms of emission reduction measures? Look at this. 8 gigaton is going to come from efficiency. You know, what is efficiency? R&D, isn't it? So research and development into combustion system. Why combustion system? Because 82% of energy comes from combustion, yeah? Then renewables, which is happening. Then fuel switching. Now, if you look at combustion science, a lot of people are working on hydrogen and ammonia, which is fantastic, okay? But just remember, fuel switching really should be fuel flexibility. In other words, I'm going to use the fuel that's available with the lowest CO2 emission at the time. So if I have natural gas available, I'm going to replace heavy fuel oil with natural gas because it has lower carbon intensity. And when I have enough hydrogen, I should be able to replace the natural gas with hydrogen, yeah? So it's a transition stage. So I intentionally here identified what needs to be done, and research and development is needed. And all of you, especially the youngsters one in here, are called upon to actually make this transition happen. In terms of what we need, again, this is technologies that exist. This is technologies that needs to be deployed, and this how money is under development. The International Energy Agency says that 40% of the technology we need by 2050 is still in the labs, your labs. Okay? So take charge and actually make it happen. And is another way to look at it in terms of the technology, what's available, what is needed, and prototypes and demonstration and so on. And let me then give you a message. Combustion is an energy conversion process. Fossil fuels are the problem. If tomorrow we replace, if tomorrow we don't sell any internal combustion engine cars, by 2050 we make no difference because there's 1.4 billion cars on the road already. The problem is the fuel, not the engine itself. Let's replace the fuel, let's make more efficiencies, yeah? Combustion accounts for 82% of energy, and by 2050 it's supposed to account for more than 50%. And I showed you that we're going to reach 2.8. In other words, combustion system is going to be in use. Combustion has been optimized and used for more than a century and is responsible for human development and advancements in society. Sustainable development, yeah? Combustion will be needed in any sustainable scenario for high temperature industrial processes, aviation and marine transport. There will not be effective electric planes, full stop. There will be some toys to play around, but they will not be effective. Most of the emission from aviation is for long-haul flights, Australia to London, Saudi Arabia to New York, and so on. Okay, and those will never run on electricity or in hydrogen for that matter. Okay, what we need to do is do SAF, sustainable aviation fuel. Okay, synthetic fuel that could actually go into the existing systems, and we could do that. And we'll use electricity to do that. But trying to change the whole system into electrification or into hydrogen for that matter is not wise in my view. Firming power networks will be needed, of course, for combustion. Production minerals needed for renewable technology. How are we going to produce the batteries? You know that a small battery in a small car, you need 150 tons of dirt to produce one battery, 150 tons. So now let's talk about the millions of cars we want to sell and how many tons of dirt we need to be able to turn to extract the metals to be able to do it, okay? So we need combustion to be able to extract all those, to build the fuel cells, to build the batteries, to build the electric motors, to build the networks, and so on. Okay, this is take-home messages. Research and development systems efficiency are needed, and we are, if we are to limit the rise. Fuel flexibility and carbon-free fuels are important to industry and transport sectors. Innovation and technology development of new energy systems are key to decarbonization. Synergies, hybridization, and fresh thinking are all needed to get there. Okay? Now, I promised Diana that I'll allow 1 or 2 questions before I go to the next section. I hope I did not dampen your enthusiasm about decarbonization, but it's good to get reality checks sometimes. The future is bright, it's just we need to make it happen and not go to what the media buzz is. Tesla will not save the world. It will make Elon Musk rich, that's about it. Please. Off? Yes, yeah, I know what you mean, yeah. Well, which will be a disaster, and it appears is going to happen. There's an interesting development, which I received an article only last week, which says that in Africa, they were able to find hydrogen underground, and it's called white hydrogen. And if this actually turns out to be true, and this is a scientific paper, if this turns to be true, it actually can have quite a step change in our approach, because currently hydrogen is too expensive and we don't have the infrastructure. But can we stop climate change? No. Do we need to start adapting? Of course we do. The cost of inaction is way, way, way more than the cost of action. I mean, I think in the 21, anyway, the billions of dollars in terms of damage due to weather change is way more than the action that we need to put in. But if we burn it, that means there's more heat to the environment, yeah? This heat is going to be trapped one way or another, because, as you know, burning methane can also produce soot particulates, which can land somewhere else. This is where the problem with flares are. See, I'm with you that there is natural sources of methane and greenhouses that we cannot control. But at least we should control things that we are emitting ourselves.
Before I let you continue, just tomorrow we will have a discussion panel between these gentlemen. So if you are interested by this kind of discussion, please join.
Yeah, hopefully that gives you food for thought. Now at least you know what I think. So there's a good reason I put this in here, and I didn't want to preempt tomorrow's, but I need to set the scene, because it's important then in you, especially the young people, of thinking what projects you're going to work on in the future, that they fit into what the plan is. The plan is efficiency, fuel switching, okay? And renewables if you want, and integration and synergies. So you need to think this way. You need to think, this is what I'm going to do, rather than, okay, electric car is going to serve the world. All right, so in terms of novel technologies, this is one technology that I've been working on for quite a while. It's called mild combustion. I'll explain it in a minute. It'll give you better efficiency, it'll give you better stability, it'll give you fuel flexibility, and give you low emission. Now, I'm ticking a lot of boxes in here, so there's less CO2, there's less pollutants, then, okay, it must be a good thing. So let's see how it works. Basically, all of us have concentrated on this yellow small region, which we call normal combustion. You have fuel, you have air, and then you burn them together. And as you know, the oxygen concentration in air is around 21%. And then here you have sort of oxygen-rich flames. And here, we're trying to deprive the flame of oxygen by diluting it with combustion products. So what I describe this is as heat and exhaust gas recirculation. You could see it as well that we're increasing the temperature of the reactants, okay? Because if we don't, and the oxygen concentration is low, the flame will not actually ignite. So then we end up with this mode in here, which is called flameless combustion or mild combustion. And it's quite a unique thing. It actually, instead of having a normal flame as you see, you'll end up with what's called a volumetric reaction. In other words, the burning is happening in every spot inside the chamber, instead of happening at the reaction zone where it's actually relatively small. So what you do in here is basically then we create the conditions by which we are diluting our reactants with products, okay, and raising its temperature above auto-ignition temperature such that there's a continuous flame. So there's no S-curve. Remember the S-curve, the flame is extinguished, and if you change it again, it's come back again. It's basically a continuous ignition. It allows you fuel flexibility over a broad range of conditions. You see in here, you know, you could, if it's above auto ignition, it will work. It will always burn, yeah, if it has enough time. And improve thermal radiation, and I'll show you why in a minute. Semi-uniform temperature distribution, and as a result of that, you'll end up with lower NOx. So there's a lot of work on the kinetics has happened. Mara Diunan from Naples, the Naples group, done a lot of work. Antonio Cavalieri did some work in here. And what they noticed is the difference between sort of the low oxygen and the high oxygen is this negative heat release that doesn't seem to happen when we have this type of combustion. And they explained the difference in the structure of these flames. And basically here they're talking about how the temperature is above the auto-ignition temperature, but the change, so once it ignites, how much additional temperature increase from the reactant temperature is below that TAI. And so this is the S-curve that you know about, and it's basically showing how a different oxygen in the oxidant stream, where you start getting basically this continuous ignition. And you could see that the reaction zone usually broadens. Instead of things happening really intensely into a very small zone, it actually happens in a bigger volume. And then, so basically denigrate this S shape, and you have gradual ignition without conventional auto-ignition, depending where you are in the system. So this is what it looks like in real life. So this is a furnace that we built. Here on the left, you have a normal flame. What we do then, and ignore the soot in here, it's not important. What we do in here is basically, before we have a fuel in the middle and air going around it. Normal flame, as you see in here, here's the flame, okay? As we reach above auto-ignition temperature, what we do, we leave everything exactly the same flow rates. We don't touch anything. We just take the air and now we inject it away from the center line. So what happens is the fuel goes into the furnace, mixes with the products, the air goes in and mixes as well. And so when the fuel and the air see each other, there's already a lot of products around. But what else? The temperature is above auto-ignition, and hence it actually becomes into the mild mode. And what you see in here is that it basically, the flame disappears. What does disappear mean? I mean, this is why they call it flameless, by the way, or colorless combustion. So what happened there is that simply there's spontaneous emissions of certain intermediates that if the temperature is not high enough, these intermediates do not emit. You could see how important the walls in terms of heat exchange between the flames. So the walls become red hot. But if you look through, you could actually see anything. Okay? The reaction is happening. Let me just repeat. The same amount of oxygen or air, the same amount of fuel. We haven't changed that. We just changed the distribution. So why are they different? One is what I described before. It's a normal flame where you have the maximum temperature. And what happens in here, when we distribute it, the temperature becomes more uniform distributed. So it's a lower temperature, but across the whole volume. Remember how before I said that the efficiency is better? Now, instead of having one region which is very hot and the rest of the regions are relatively cold, now we have the whole furnace as at a moderate temperature. And if we integrate under the curves, we'll find that total thermal radiation increases, and that's why the efficiency is higher. And more uniform, of course. Here's another way to prove the point. So we done experiments on all of this. Methane, ethylene, propane, oxymild. In other words, instead of putting air in, we put just oxygen. Solid fuels, brown coal, black coal, sawdust, grape bark, almond husks. All of this burns inside this same furnace. Okay? And you could see in here that the amount of CO2 sort of with the oxygen in terms of to try and prove our point. And then we go from these ghostly flames or full flames all the way to what we call flameless, and even at basically a pure oxygen coming in at 5.5 all the way up to 5.1. So now we're burning stoichiometric oxygen only fuel under mild conditions. So this is what fuel flexibility means. System that can take anything you could throw at it, yeah? Here's another way to look at it in terms of energy release and activation energy and heat release. And then it shows basically what happens in this case where it's mild combustion, and then where here you have not combustion, and this is where the ignition is. And you could see in here that these are all the different experiments that were done, and the numbers in here is actually really the oxygen concentration in the oxidant stream. So this is work we done. We're trying to understand this. Inside the furnace, it's really hard to make measurements. So what we did, we took our jet, we're surrounding it with a big pilot. This pilot had the same products of the jet, okay? We're saying if this fuel burns, what would it produce? It would produce CO2 and water and nitrogen and oxygen and so on, or in the exhaust, that is. And then we ran different fuels in, and we tried to basically replicate the mild condition, but under a simple geometry, so we'll be able to do laser measurements in here. So this is the type of burner that I built. I called it jet in a hot core flow. The core flow is really products of combustion. And then what I have the ability to do is to change the amount of oxygen in by trading sort of air with oxygen and nitrogen, and be able to then decide how much oxygen is this jet in here you're going to see when it actually emerges. And you could see in here that at 3%, no matter what the fuel is, I'm actually having in the bottom part, I'm having a flameless oxidation. In other words, the flame is disappeared. When I show you some measurements where actually it is replicating these mild conditions. As you go to the 9% case, you'll end up with a normal flame. And for all these conditions, and this is repeated again in here for 3% and 9%. So while you don't see anything here, if you zoom in, really, you may see a faint flame in there, but this is because the temperature increase is relatively small as compared to a normal flame. So we've done a lot of measurements in this, both from mild flames as well as transitional flames. And we threw everything at it from Raman-Rayleigh Leaf to a lot of measurements. I won't bore you with the details, but basically we were trying to understand the structure of these flames. This is the laminar flames. This is the turbulent flames that we looked at under different conditions. And this is the mixture here is CH4H2. And we went to Sandia and we done single point Raman-Rayleigh measurements with Rob Barlow. We built our own looking at imaging for temperature from Rayleigh, OH LEF, and CH2O from PLEF. We also done, some of them have sooty flames, so we measured the temperature and the soot, as well as the OH as well, and that's all done at the University of Adelaide. And so what we basically operated at is that the core flow was anywhere between 1100 to 1600 Kelvin, so above autoignition. The oxygen was quite a wide range. This is the velocities that we ran. And then this is a jet Reynolds number up to 30K. And we done all these fuels as well. And we also changed the composition of the admixtures that we did to the fuel as well. Here's some of the data from single point measurements. So you could see in here, irrespective of the Reynolds number, the OH, the CO, and the temperature is roughly the same. In other words, this flame will burn. Doesn't matter what you do to it in a way. Of course, there's minor effects of turbulence chemistry interactions that you could see, but you could see that the levels of OH is relatively low, and that the flame is fully burning, and there's no extinction, of course, as you would expect. Here's another measurements are done at Aachen with the late Professor Peters, where he had a similar furnace, the one that I had, and we discovered this crossover temperature. It's interesting, when we done these measurements, we ended up with these small islands. Later, DNS people called it pancakes. But basically, there is these two color systems. And when we done the statistics, we found that there's a bimodal distribution. In fact, there's a third one in here, which we ignored. But what really was interesting is what happens at 1300 Kelvin. And this is in methane. It's called the crossover temperature between the reacting and the non-reacting. We also done, the Japanese have sort of looked at what's the best way to do it, and they had this alternating recuperative systems by which they heat the oxidants coming in, and then when they return it, so this system would actually take heat from the exhaust and vice versa. What I wanted to prove is that you'll be able to do it in situ, inside the furnace itself, and also that dilution of the fuel can help you achieve mild combustion without having to extinguish the flame due to strain. That was the concept. So what we try to do is basically mix some inerts with the fuel and show that actually we will be able to reduce the NOx, and this was taken as achieving mild combustion up to 0, depending on the level of dilution that we are putting into the system. So we looked at alternatives. We built a new furnace, and we wanted to understand pressure. We wanted to understand more complex fuels. And we sort of ran these different experiments using that. And here's some of the details for some of the fuels that we used. And you could see in here that we basically looked at the structure, looked at the soot and at the temperature, and how it's actually affected by these conditions, and then try to understand why at higher, more complex hydrocarbons we were getting these soot formations, and so there became a whole sort of new things to understand soot under diluted conditions as such. And then we done effect of pressure, and you could see here how the pressure has increased. And we were looking at the effect of pressure on the emission of NOx at different equivalence ratio. And you see here that actually we're able to achieve all the way down to 30 ppm, even at high pressures, depending on the operating conditions, using fuel and a carrier gas in this case, and a primary. And this work was done with Heinz Pitch in. We then shifted to actually build our own furnace. Once we try to understand what happens in these sort of more canonical flames, then we built this furnace and we used it. I explained to you before how we took the fuel from the center to the edge, and then how these things in between were actually the exhaust gases, and then how we actually were able to feed other gaseous mixtures in, or solid particles carried by either nitrogen or CO2. And by the way, here we were actually also extracting energy. We were able to extract 40% of the energy without any problem. And we had windows and points to actually measure temperature. So this is what the furnace looked like, and the heat exchanger, and we had a cyclonic ash collector when we done solid fuels. And some operating conditions, particularly in sawdust, and I want to show you some pictures in here. So you could see that we actually were able to burn solid fuels using this. I mean, it's remarkable that you'll be able to do that. We were able to identify some visible flames depending on the operating conditions. But that's particularly when we carried the sawdust with air into the furnace. But when we carried it with CO2, the whole thing disappeared, basically. You could see a few dots here and there of big particles that are burning. But in essence, we're taking solid fuels and we're running it flameless, okay? And then the NOx was done, and we were really sort of happy that we were able to have one furnace that can actually operate under all these different conditions. Okay, well, we also looked at coal, and I know people are going to charge at me, why do you use coal? But at the time, we wanted to understand if it also works for coal and if it can reduces the impact of sort of coal. We also looked at temperature distribution inside, and this is one thing about this system that is very, very homogeneous temperatures inside, irrespective of what type of fuel you're using. I won't bore you with all of the details, but you could see how the uniformity of the flow within the furnace, within sort of a relatively less than 100 degrees difference between them. And we measured NOx, and we measured sort of at different conditions. And we were trying to understand if there's any rebound mechanism. So we concluded that because there's high temperatures, there's likely to be a rebound mechanism because we were measuring high concentration at one point, and then we were measuring lower concentration in the exhaust. And then we compared those, and we tried to understand where the NOx is coming from. And you could see actually that thermal NOx is very small because the temperatures is relatively low, but that fuel NOx is actually is substantial. And that's fuel that comes, basically that's nitrogen bonded to the coal, and that the rebound is also active as well. And, you know, we compare them against each other in carbon consumptions and so on, and depending on what carrier do we use. We built another furnace, which is much bigger and more flexible in terms of the feeding system. And we tested that as well at a much larger scale. Now we actually start looking at biomass, grape mark, almond husk, and brown coal as a comparison. And then we done all the analysis for them. And I wanted to show some of the results in here. So you could see that actually we could also achieve mild combustion using biomass as well. We looked at temperature distribution. Again, the message about uniformity of the temperature is there. And, you know, which is most important, we found, you know, to be relatively high, but in the scheme of things, it actually wasn't too bad, and compared to other systems, of course, mostly because the temperature was kept at relatively low value. Then we compared them in terms of CO, in terms of NO, in terms of oxygen, of course, at different conditions, and how much of it is left in a way. All right, so we ran mild combustion, and mild combustion works. It has been commercialized. It gives you fuel flexibility, it gives you efficiency, it gives you reduced emission. Then we came and said, okay, well, that's good. What else can we do with it? And we came up with this concept of introducing renewable energy into combustion. So we done this hybrid solar receiver combustor. What we basically said, the synergy between high temperature achieved through concentrated solar and combustion itself. Can I put them together by which I could operate the same receiver either when the solar energy is available, and if it's not, I'll put the shutter on and turn the burners on. And inside, we actually run mild combustion to give us the heat transfer that we required. So when you combine this as compared to two separate systems, you'll find that you have reduced capital cost, one system, not two. You reduce heat losses. You only heat losses from one system, not two. Reduce startup and shutdown losses. So if you have this receiver, during the day, you actually collect energy and it's hot. You're basically going to leave it all night. And you can come back again in the morning. So that's going to cool down. So this is energy lost. So you need then to compensate for that energy. Increase harvesting of low flux. In the morning, it takes time for things to heat up. And if you need a minimum temperature, you can't start until you reach the temperature you require. With combustion, you could turn in a moment and start basically maximizing on it. Options to reduce trace heating, flexibility of different applications. So it has a lot of advantages. We built one. We had it's actually a cinema projector that we used, a 5 kilowatt, where you directed the energy into the furnace here. And when that wasn't operational, we actually put the burner through this system to heat it up. And we had a heat exchanger to try and look at the heat transfer at different positions. And you could see in here, we ran it on really different hydrogen, LPG, natural gas, a mix of those. And we done some research, modeling of syngas and ammonia. So bottom line is the efficiency can be as high as 90%, that we could achieve temperatures of up to 750 degrees C. And we could operate it continuously in that both solar and combustion, and then that the convective losses through the aperture were less than 50% of radiative with no wind. And you could see in here that we ran it on renewable fuels. So syngas can be produced from biomass sources, hydrogen, of course, in there that you could produce and use. Some CFD, I won't go into much details, but again, emphasizing the point of homogeneity. And of course, we looked at the Damkohler number, which is an important component in is that the Damkohler number is relatively low, closer to 1 at least in these conditions. And then we looked at heat transfer, and they wanted to find the efficiency of those for the different compositions of hydrogen to CO. And then basically we compared those for different applications and to realize how much radiation is happening in there in comparison. As more CFD for hydrogen and ammonia. And here's the key outcomes. Mild combustion successfully stabilized for hydrogen, syngas, and ammonia. Found that the Damkohler number is less than 1, low NOx and uniform temperature. For syngas, CO acts as diluent in comparison to hydrogen case. Decrease in hydrogen CO leads to, that's the ratio, decrease in maximum Damkohler number, mean gas temperature and reaction rates. Broaden the reaction zones and shift to closer to outlet section. For ammonia, decrease of maximum Damkohler number, mean gas temperature and reaction rates, and so on. You could see here where our emission was relatively low, and this is the NOx and where the NOx is coming from. All right, so another message in here is that combining, integrating or hybridizing renewable energy with combustion systems is one way to increase the penetration into the system. Renewable is expensive, renewable is intermittent, okay, but is necessary. The way to introduce it is not to shut everything off and build something new, it is to actually integrate it. And if you can, within the same system, you save in terms of the capital cost, and you actually provide what's called firm supply, guaranteed. Where this idea came from is we were talking to industry. Industry want heat or power 24/7. They don't want it just when the sun is shining. So this allowed us to do that. Okay, now, let's switch to something else. I have half an hour, yeah? Switch to something else, and then how do we use hydrogen in industrial furnaces? As you know, many of the fossil fuels produce soot, and this soot actually radiates, and then a lot of this radiation is used in industrial processes. Hydrogen flames do not radiate. In fact, it's fossil fuel-based flames radiate roughly 40% of its energy, while hydrogen is only 10% of energy. So if I'm going to replace fossil-based fuel with hydrogen, I need a way by which I could increase the radiation characteristics. So we came up with this concept. If I add bio-oils of biofuel to hydrogen, I should make the hydrogen flame radiate because I'm going to have soot within the flame. And then it has two effects. One is increases the radiation from the flame. Two, it lowers the gaseous flame temperature, which means reduces NOx. And three, this soot will burn within the flame envelope, okay, because this is hydrogen and burns on the lean side. So basically, all of it is going to be burned and not emitted into the exhaust. So then we had a project looking at how do we make hydrogen flames radiate more. And we blend it either vaporized or in spray mode. We started with toluene because we understand it. Later on, we shifted into bio-oils. And then we ran these flames. We done some diagnostics in it. This is how the flame looks like, depending on S means spray, V means vapor. And then you could see here 1%, 3%, 5%. This is 1%, 3%, 5%. And this is depending on if it's spray or vapor. And you could see here when it's spray, it's actually high radiation or high soot, mostly because you're creating localized rich mixtures that actually giving you the soot formation. We've done some measurements of well, these are some calculations actually trying to see how is the contribution of it to pH to try and understand actually what we have seen. And some of it is basically a collective pH signal to indicate the precursors to combustion, to soot. And then we looked at the mechanisms and identified sort of the different components that are responsible. A2, formaldehyde, and CO seems to be the major players in here of how to, for pH to form. And then we wanted to sort of see which components are contributed most and why. And that's specifically for toluene, by the way. Then we looked at the trends of the addition and then came up with the idea that there is difference between doping and blending. Doping is at low concentration, blending is at a high concentration, and those behave in a different manner to each other. And then we looked sort of at the ratios of formaldehyde to A2 in terms of rate of production as percentage of toluene dopant to try and understand the mechanism and why is actually the amount of soot changing. Particularly, it's nonlinear with toluene addition. So what we're finding from this is that experimental measurements show soot volume fraction increases nonlinearly with small concentration of toluene. That addition of toluene to 3 to 5% result in significant soot loading with little change in OH concentration. Basically implies the flame still burning and then all the soot is going to be oxidized. Explained by rate of production and pathway analysis of formaldehyde and A2. And combined results that suggest that nonlinear hydrocarbon doping regime should be considered separate to blending. In other words, the low concentration, high concentration behave differently. All right. Any question? Yeah.
The CO2?
Well, you mean when you're blending to increase the CO2?
Well, you blend in PAH and then you
No, sorry, we didn't blend
CO2 out.
We put toluene into the fuel and then we measure the pH.
But you get CO2 out.
Yeah, but if it's coming from renewable sources, then the CO2 is neutral. The idea is that we're going to put biofuels and create soot.
Okay. Okay.
I understand, yes, of course. If you put fossil fuels in, you're going to produce more CO2, yes. But if this blend is coming from renewables, then from biomass, then you don't have a problem.
I have a question, actually. You show us some really nice results about mild combustion. Mild combustion has been studied for more than 20 years. And do you have examples of this new technology translating to industry? And my second question is about the interesting work that you have done on the combination between solar and combustion. Did this also translate it to industry? Do you have example of that?
Thank you. Mild combustion has been commercialized, not to the extent it should. It's mostly done with reheat furnaces and also heating tubes. In fact, I'm writing a review paper, and this is exactly what we've done. We collected some information about commercialization. It should be done more. It is, to some extent, because of the way you need to introduce it, a little bit niche, but it has a lot of potential, more than it's. One of the major issues that you could do is intensifying. If anybody wants to get their hand in a really difficult problem, is how do you intensify this process and run it inside a gas turbine combustor? Because if you could do it at pressure, at a small scale, then you actually can avoid all the thermoacoustics instabilities. You could run at much later conditions and more uniform temperature. And actually, this has much more advantages from NOx emissions and other things as well. And your second question is about commercializing
the solar heating.
Solar. We do have a patent in this. It has not picked up, mostly because concentrated solar is still more expensive than PV. The trend of cost of concentrated solar is going much faster than the PV ever did. China has came on the line now, installing hundreds of megawatts of concentrated solar. And as you start scaling up, you could then automate the process. 40% or more of the cost is actually the mirrors. If you could automate that, then you could actually have an advantage. Of course, concentrated solar have the advantage of thermal storage, which actually can also help. But it hasn't really made it commercial yet. Yeah. Please. Yeah.
I have a question. So you talked about you produced or designed 2 furnaces, I think,
Yeah.
or more. So what's the criteria into finalizing the design of that furnace? What type of material do you land to use in the end? So are we talking Hastelloy, or is there more exotic material?
No, we didn't have to go that far. So first, let's remember these are experimental burners. Okay, so what we did is we built it from just normal steel on the outside, 3 millimeter thick. But inside, we put some sort of silicon oxide type insulation material, around 50 millimeter thick. So we lined it all up. This material is relatively light, is a good insulator. And because the outside is also open to the environment to be cooled, so we calculated the heat losses, and it's something like 8%, 10%. But as long as we were able to establish steady state temperature inside, we were good. So if we put some bricks inside, as you would in normal furnaces, it will take us hours and hours to heat it up and become stable. While with these sort of sheets, it actually only took us some 35 minutes, 40 minutes, and the furnace was at constant temperature. So it worked for us quite well. Yeah.
So you're talking about the small furnaces. So how small did you reach the 30 or 40 minute steady state temperature? Are we talking about 30 centimeter diameter or smaller?
So we were running it roughly at 20 kilowatts. Is that what you're asking?
No, the diameter of the furnaces.
The diameter of the furnace?
Yeah.
So one of them was 250 by 250, and the other one was half a meter by half a meter and 1.5 meter high.
Okay.
And we were running it around 50 kilowatts. Other questions? Okay. Well, if there's more, we'll do it at the end. So another idea is steam calcination. I'm not sure how much you know about producing steam. So what you start with is limestone, calcium carbonate. You're basically provided with heat, and then you create calcium oxide and CO2. And your calcium oxide becomes cement. Okay? Now here you have 2 sources of CO2. The first one is in the heat you need to generate to be able to do what's called the calcination. And another one is the CO2 that actually is separated from the calcium carbonate. So you have two sources. Roughly 40% comes from the heat, and 60% comes from the process itself. Okay? So you look at this and saying, okay, where can I make a difference? Yeah. So of course, if you're here burning fossil fuels, what you're going to end up with is water, CO2, nitrogen, and maybe some oxygen. Okay. So one of the major issues with capturing CO2 is separating it from nitrogen. Remember that. It'll be useful for you in the rest of your career. Separating nitrogen from CO2 is a problem, and it's a costly problem. Yeah? If I can avoid nitrogen, then I'm in the winner. So one option, what people did, is they did here what's called oxy-combustion, oxy-fuel. In that they take oxygen and fuel. Okay, let's say CH4. You'll end up with water and CO2, so there's no nitrogen. So what you end up in the exhaust then? CaO, which is a solid, CO2, which is a gas, and H2O, which you could condense. Eventually, basically, you could separate all the three of them with very little cost, yeah? Just you need to recover the energy. So we came and said, okay, well, how else can we supply this heat in here without introducing nitrogen into the system? So we came up with the concept of steam calcination. What steam calcination means is that you basically here start with hydrogen and oxygen. You burn them, basically you go through your reactor into the, basically then the calciner, and then you basically recover your water, you recover your, you catch your CO2 and your calcium oxide. And then we looked at how can steam be generated. So we have this concept. I think I have a sketch of it here. Yeah, here it is. So you start with water. You start with water and renewable electricity. You put it through an electrolyzer. What the electrolyzer is going to do is going to split the water into hydrogen and oxygen. What you do then, you bring them into another combustor here, and then you add more water. And what you end up with is what I call green steam. Why is it green? Because the source of the energy is renewable electricity. Now, these things are roughly 70% efficient. So the first thing you need to know is that you lost 30% of your energy. Okay? But what you could do from there on is you could dial the temperature you want. It's a relatively small system. You don't have any heat exchangers. Okay? You just need the material to withstand steam at a high temperature and potentially a little bit high pressure. So this is where we think the steam is going to come from. In other words, I don't have to store hydrogen, I don't have to store oxygen, I only have to store water, and once I have electricity, I should be able to generate my steam. So basically, steam can be generated through the combustion of this. Using steam calcination requires lower temperatures and hence reducing energy per ton of lime. Why do we need lower temperature? Because we have less CO2. Remember, we're trying to remove the CO2. So equilibrium works with you now. If you increase the CO2, that means you have to calcine at a higher temperature. But if you reduce the CO2, then you calcine at a lower temperature. As I said, hydrogen and oxygen can be produced through electrolysis. Condensing steam will leave pure steam of a stream of CO2 to be captured and stored or used. And here's the important part. Our ASPE model shows that we could recover 90% of the water and 94% of the CO2. Current systems of amine systems to capture CO2 from the exhaust at best can give you 80%. So 20% is lost, okay? Here, we could actually go up to 94% of CO2 captured. And the good thing is as well, we could recover a lot of the water. So we could use it again. And then we went on techno-economics, and we found it will be financially viable if we compare it to natural gas plus capture, when the price of hydrogen is around $2.2 a kilogram. Of course, we're heading to $1 a kilogram, supposedly. So then we're going to be viable relatively soon. Now, this process actually can apply to other things, not just also to limestone. So I won't bore you with the details. Basically, we've done analysis of what the price of natural gas needs to be per gigajoule for sort of the hydrogen to be viable. And we looked at different combinations of things. But the bottom line is that if you reach the $1 per kilogram, you are in safe hands. And here's so what the added cost to the limestone is. And you could find in here that the added cost is not substantial as compared to business as usual. depending on the fuel cost, of course. All right. So the last thing I want to talk about, and I will do it quickly, is H2O2. According to the International Energy Agency, we're going to be producing 600 million tons of green hydrogen by 2050. Now, for every ton of hydrogen, we're going to produce 8.8 tons of oxygen. So we're going to end up with 5,280 million tons of oxygen. This is 5.28 billion tons of oxygen. Now, if this oxygen is to go to the environment, it will be harmful. It will affect the ecosystem. It will increase corrosion. It will affect plants and animals. So this is not a good thing. Then we're going to say, okay, so what do we do with this oxygen instead of just releasing it to the environment? So venting is no good. Then what we decided to do is to use renewable electricity to convert oxygen into hydrogen peroxide, and then use it as an oxygen carrier. Because the other two options is to either pressurize it or liquefy it. And when we do, we also need to find a reason or a place to use it, not just produce it. So, and then you could also use it to do SMR, ATR, which needs both oxygen and steam. So here's a little bit about H2O2, which is many of you would have seen in supermarkets. You buy this bottle, it's a very good cleaner because it gives you this oxygen that you could need. So I won't talk a lot about it, but currently it's produced in low concentrations, and it's actually harmful. At 100%, H2O2 is a rocket fuel. It's because when you bond the water and the oxygen, you store around 5 megajoule per kilogram. And when this energy is released, it's like a fuel. In the past, H2O2 was added to the fuel as an accelerant. What we decided to do is to use it as an oxidant, not as a fuel. You could see in here, in terms of percentage, H2O2 contains 47% by mass of oxygen. So it is an oxygen carrier. And when it's, of course, where H2O2 dissociates, it will give you this oxygen back with energy as well. So flame stabilizer to enhance the reaction rate and flame burning velocity through increasing activation and intermediate radicals. That's a well-known thing, and it's been researched before. So this is where I've been used. I don't want to go through all the different usages. It's not produced at millions of tons, but it's quite popular and available. Currently, it's produced through this process called anthraquinone, and which basically 95%. But for every ton of H2O2 you produce, you emit 524 kilograms of CO2. So it's actually producing H2O2 today. It's harmful to the environment. But what we're thinking is that you could electrochemically actually produce it, or photochemically, and then use that to combine water and oxygen and then carry it this way. So I don't have a lot of time for this. So this is 534 kilograms of CO2 per kilogram of H2O2 today. So even if we don't sort of valorize oxygen, if we can't find another process to produce H2O2, that will be harmful, useful for the environment. Okay, again, I'm going to skip all of that. I don't think it's for a lot of interest. This is how you produce it. This is the process again. Okay, so these are the value chain of what do you do with H2O2 once you produce it. So we basically reduce risks of stranded assets. You could reduce life cycle of CO2 and non-CO2 emissions, and so on. There's a lot of options, but what I want to focus on is really combustion. So here's what we did, and Jun is here in the audience. It's his PhD project. Basically, what we did is we took H2O2, mixed with water at 40% by mass, and we burned it against fuel. And surprise, surprise, this fuel actually burns quite well. And I could see in here that with 40%. And then we changed the fuel composition, and then we end up with really a stable flame that we were able to measure. To try and understand the chemistry of it and the contribution of the oxygen, we also done a steam and oxygen, both at the same temperature, and then to see what's the effect of the energy release from the H2O2 dissociation on the flame itself. So these are some of the flames. One is with H2O2 and water, another one with oxygen and water, and you could see these flames are happily stable and resilient. We've done extinction measurements to look at what happened to these flames as the oxygen concentration decreases or increases. So this is a normal pure methane flame running with 21% oxygen or reduced oxygen. And this is actually when we try to run it at different oxygen to steam concentration with the hydrogen-nitrogen mixture to try and understand sort of the extinction characteristics with this as the oxidant. Here's another laminar flame runs that Jajundin did, and it shows in here the double peak of heat release from H2O2. One is when it dissociates, another one when it reacts. And so on. So we're also running a swirl burner, and we're trying to build that and use it. I'm going to skip all of this, Diana. This is CFD of these flames. And go to the last slide, which is the conclusion. This is some of the work we've done already. Actually, H2O2 can be used for steam calcination as well, for lime calcination as well, because it gives you basically water and energy, and then you could steam and energy, and you could actually use it this way. Again, it produces CO2 and water, and from there on, we could actually separate, remove the CO2 and the water and the calcium oxide. Again, this is a patented technology. I won't go into it in too much details. Let me skip all of this. Summary: high cost of CO2 capture, needs for separation, dilution from CO2 and nitrogen. We need something without nitrogen in the exhaust. A primary assessment concept of this approach seems to be working. We need to do techno-economics. We're eliminating any NOx is not well established, and scientific knowledge is lacking. This is why we're doing the research, and we need to understand the fundamentals and so on. So here's the final thoughts. Combustion is key to sustainability. Get this into your head, tell it to everyone you meet. Mild combustion offers solutions to many current problems. Hybrid of concentrated solar and combustion is feasible. Steam calcination offers an avenue to decarbonize cements. Hydrogen peroxide as oxygen carrier and oxidizer shows good premise. Innovation and out-of-the-box thinking will basically lead to impact. Thank you for your attention. I'll be happy to answer any question about any of this.
Thank you, Bassam. Do you have any question? Okay.
There's people online? Or?
Yeah, thank you, Professor Dally. I had a question. You mentioned that there is an important problem we should keep in mind, which is separating CO2 and H2. Is this only a problem with cement or other industries?
CO2 and nitrogen.
Sorry, nitrogen.
The nitrogen is when you burn with air, you're going to end up with nitrogen. No, this is a problem for every combustion system in the world. Once you use air as your oxidant, okay, you're going to end up with nitrogen. There's another problem with nitrogen. Remember, you're bringing in an oxidant, yeah, which is 79% of your mixture is an inert. You're heating it up to 2000 degrees and you're cooling it down, okay? You're not using it for anything. It's actually sucking energy out of the system. It's not participating. So if you could eliminate the nitrogen, then you actually you have much more efficient systems, and then you don't have to then spend a lot of energy and cost to separate the CO2 from the nitrogen. And this is where the problem is.
Okay, and your proposed solution was using the steam. Is cryogenic capture also a possible solution for this problem?
You don't need it here because the only thing you need to do is to condense the water, okay? And then you'll end up with CO2 as a gas. And because the calcium oxide is solid, then you could collect the water, CO2 you could collect, and the calcium oxide you could collect. You have no, it's just simple heat transfer from there on. It's a relatively simple system, a heat exchanger you need.
Okay, thank you.
Hey, thank you. So you talked a bit about hydrogen peroxide and its kind of development or lack of development. What do you think the top barriers are for technology translation for hydrogen peroxide?
So the major problem with hydrogen peroxide is that with electrochemical ways, it's hard to produce more than 2 or 3% concentration. So the natural way hydrogen peroxide does is actually it releases its oxygen back. It's not sort of the bottom energy state. So you're trying to keep this oxygen attached to the water. So what happens is that you produce it, but it's just the reaction go backwards most of the time. How do you keep it attached? Okay, is where most of the challenge is electrochemically. Now, there's people thinking about plasma, people thinking about innovative way to do it at lower temperature. Is a lot of, even lower pressure, lower ways to try actually achieve this because the price is quite large if you can achieve it.
Thank you.
Thank you, Professor Bassam, for your nice talk. So you mentioned about steam calcination, right? And the main purpose, which I understood, is to reduce the energy constraint, the number one. And number two is the production of pure CO2. When you separate the water from it, you get the pure CO2. But I think I read a paper published by MIT, I think 2 years ago, where they deal with an electrochemical reduction of CO3 to produce calcium oxide. And so what their aim is they apply electricity in an electrolyzer, and calcium from calcium carbonate will move to the cathode and will precipitate as calcium hydroxide or calcium oxide. And they can use that combining with the silicates, you get calcium silicates for the cement industry. And so if you use renewable energy, everything is green actually. So you are not producing any CO2. And they're claiming that you need only low energy than the thermal regeneration of CO3. Yeah, so I just thought about it and maybe let you know aware of it.
Yeah, well, thank you for that. So with these systems, the issue is scale. How easily can you scale an electrochemical system to work at what we require? By the way, cement is 8% of all CO2 emission in the world. Anywhere between 7 and 8, along with steel. Now, if cement was a country, it would be number 3 in the world in terms of CO2 emission. It's a substantial amounts of cement. And by the way, China produces, don't quote me on that, something like 8 times more cement than the next 10 countries combined after it. I mean, the amount of cement that's produced in China is enormous. So the smallest reduction in CO2 emission makes a lot of difference. What I haven't mentioned in here, and I've been looking at cement for a while, is that there's ways by which you could replace limestone with clay. And when you calcine clay, you don't emit CO2. And you could actually replace limestone by 40% with clay. And with this, you reduce CO2 by 40% almost immediately. So this part is unrelated to the combustion or to the heat. It's just related to the material itself. They created something called LC3 or triple C, and from EPFL in Switzerland, and they made it the IP available to anyone to use. It was approved in lots of countries in the standards. It's just this industry in particular is very conservative and have not moved in that direction. But clay is available all over the world in huge quantities and can be used, actually. And that's another way to do it quite quickly. Yeah.
It's a question from one of the online attendees.
Yes.
So the person is asking, are you working on exhaust dilution for ammonia combustion?
Ammonia combustion. What's the one before?
If you're working on exhaust dilution for this type of combustion.
Yes. Yes. I have a project on looking at ammonia under mild conditions, and this is where dilution comes in. It offers a lot of advantages, mostly to reduce thermal NOx, but there's a way by which we could activate, hopefully, and Professor Kobayashi can correct me in here, is the reban mechanism, hopefully. So we can't control the prompt NOx, but maybe we could find ways to actually reban some of it before we have to clean it from the exhaust. But yeah, the answer is yes, yeah.
So I think it's time to thanks again, Professor Bassam. So tomorrow we have an interesting day. I don't know if you remember, but at the first time of my first talk at the lecture, I was explaining that we will have 4 important parts in this summer school. The first part are the lectures. Second part are the lab tutorials and the hands-on. Third part is networking. And the fourth part is professional development. Tomorrow is more about professional development. I hope you will attend. In the morning, you will have a workshop about professional development. This is something that is really made for you. This will be part of how you can grow in your professional career. And then we'll have a second part where we'll have Professor Bassam, Professor Marcus, Professor Joao, and Professor Kobayashi that will give that will discuss about the future of combustion. They are coming from Australia, Brazil, Europe, and Japan. And I hope we'll have an interesting discussion about the perspective of combustion in these different parts of the world. So thank you very much and see you tomorrow.